I'm Xavi, the head of technical documentation, and I will be showing you the details and a live demo of the state connector. So let's start with the basics. What is the state connector? It is a smart contract running on the Flare blockchain that can retrieve information from outside the Flare blockchain. So it basically works like an on-demand oracle. As you can see, any user on the chain and outside the chain can request things to the state connector, and they will get replies from the state connector. And what the state connector does is goes outside, goes into the world, fetches the information, and sends it back to the requester. It only answers to yes, no questions which are objectively verifiable. That means that it can't answer any kind of question. It has to be objectively verifiable. And also, it does it very quickly. That means that it has a level of scalability that's comparable to Web 2. It's nothing like what we are used to see on Web 3. Why is this interesting? Because if we are able to retrieve the state of other blockchains, we can do things like checking whether or not a transaction happened on another chain. And if we are able to do that, we've got a critical building block for things like the F assets and the layer cake bridge that we have just described. So it's a very important piece of the Flare ecosystem. And how does it work? How can a smart contract get information from off chain? Well, it does it by using the attestation providers. The general scheme is that requests go into the state connector and they are forwarded to the attestation providers. Attestation providers are independent entities. They are pieces of software running outside the Flare blockchain. They are not managed by Flare in any way. They are just computer programs running on somebody else's computer that receive the requests, go into the world, fetch the information, submit the information back to the state connector, so it gets back into the blockchain, and then they get rewarded for this, obviously. And then the state connector runs a consensus algorithm. So all the answers, independent answers that it gets from all the attestation providers, it runs a consensus algorithm, and if more than 50% of the answers agree, that's the agreed upon answer, and it's made public so that whoever requested that can get the answer. And we are going to show all this using a live demo. Now, the live demo has a pause of about 5 minutes in the middle because there's consensus involved. The attestation providers need to go into the world, fetch information, and bring it back, and then they need to be evaluated. So during this 5 minutes pause during the demo, I will be giving you the exact details of how this works. So the demo, we will be making a transfer into the Algorand network. We could have used the Bitcoin network also. We've got that already implemented, but then the demo would have taken a bit longer. So we use the Algorand network. And once the transfer is done, we will request the state connector whether that transfer has happened or not on a different blockchain. So let's start the demo. So I pass the baton to Luca.
Yep. Hello. Thank you, Xavi. Hello, everybody. I'm Luka from a smart contract team, and today I'll be doing the state connector proof of concept. In reality, most of the work and filling out the forms and querying the data from the underlying explorers this is all gonna be automated by the third-party applications that are gonna be actually using the state connector protocol as part of their infrastructure. And as Xavi mentioned today, I will be using one of the supported attestation types called payment transaction. We already have that implemented for 5 different underlying chains. So Bitcoin, Litecoin, Dogecoin, XRP, and Algo. And for today's presentations, I will be using Algorand's blockchain to transfer some of their native Algo tokens. Okay, so let's begin. First off, I'll go to my Algorand wallet. I'll make a transaction on Algorand's blockchain. For instance, I'll send 2 Algo tokens to back to myself. So I'll put receiving address as my address. I'll put in some node to my transaction. This node can later be used by the state connector system and everybody using it. And note that this payment transaction starts with 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And we will later be able to see this. So yeah, I'll create a transaction, sign it, and send it to the world. And now let's go back to the state connector system and see how dApps using the state connector as part of their infrastructure actually validate this data. So on your screen, you can see 7 different attestation types. We can add more of them by governance system. We already implemented 4 of them. That's payment transaction, balance decreasing transaction, block height confirmation, and referenced payment non-existence. These are the attestations that are going to be used by the F-asset system. And we also added 3 more examples to show off state connectors' versatility and scalability to bring data from Web 2 to Web 3 and from other Web 3 platforms to Flare. So we can bring results of a chess match to the state connector system, or prices of different stocks to the state connector system, or even validate some NFT transfers that happened on other chains. For the demo that we're doing, the third-party application would request a payment verification, and for the source, we would have to specify Algorand. And now we need to get some data from the Algorand's blockchain. For that, I'll go back to my wallet. I see my transaction that I created earlier, and I go to view it in Explorer. In order to prove this payment transaction, I have to provide transaction ID, and also the hash of a block that's at least 3 blocks newer than the block that my transaction was a part of. So, for instance, I'll take this block that happened 5 blocks after my block, put its hash here, and go back, copy the transaction ID, and put it here. And now the dApp would create a request to the state connector system. User would have to sign this request, and now this request was sent to the state connector system, and now we have to wait for it to be validated by attestation providers. And this is now in state connector's request commit reveal phase, and Xavi will explain this in more detail.
Okay, thanks.
Back to you, Xavi.
So if we can see my presentation, thanks. So what did we just see? We made a request to the state connector that was filling that form with the transaction hash and the block height at which the transaction happened. And that information was sent to the state connector through a request. It's a normal transaction, so it had to be signed with MetaMask, as you've seen. What's happening now, this request is being forwarded to all the attestation providers in the network. This is using EVM events, so it's very lightweight and easily scalable. The attestation providers right now are going into the world and fetching the requested data and submitting the data back to the state connector. Now, let me use this time to explain a bit how this is done. Data is collected in rounds. So every time a user makes a request, the attestation providers do not jump on it and start fetching the information. Instead, during a 90 seconds round, requests are gathered, and once the round is finished, the information is fetched, and all the requests made during that round are answered at once. And that's done by building a Merkle tree. As some of you may already know, a Merkle tree is made up of the hashes of hashes. We are actually hashing the request and the answer to that request and building a tree that compresses all these answers into a single Merkle tree root. That is a single hash that summarizes all the information that we are answering. Once an attestation provider has collected all the answers for that round, it builds the Merkle tree and submits the Merkle root, only the root. That makes this system extremely scalable because that means that we can answer lots and lots of questions of requests, and we only need to transmit a single Merkle root every time. Once the state connector has all the answers from all the attestation providers, meaning all the Merkle roots, it just counts how many different roots it received. And if more than 50% of the roots are the same, that's considered the agreed upon result, and it's made public. If there's no agreement, if there's not more than half of the attestation providers providing the same result, then that result is not made public. So no result is given. That round is considered void or null. So if you made a request and you don't get an answer for that round, you have to make the request again. At this point, maybe the demo has already the results.
We need 60 more seconds.
Okay, I can keep talking then. I wanted to talk about a couple more details. I wanted to talk about this a bit later, but let's do it now. Further optimization is that all the requests are made in 3 phases called request, commit, and reveal, and that's why this is called the RCR protocol. All the user requests are received during the request phase. The attestation providers submit their results during the commit phase, but these results are obfuscated. They are hashed by an unknown key so that the different attestation providers cannot pick at each other's submissions and cheat. They cannot copy the results of some other people and get rewarded by not doing any job at all. So during the commit phase, the results are sent obfuscated. And then during the third phase, the reveal phase, attestation providers provide the deobfuscation key so that the state connector can actually see the results and run the state connector. And this is to avoid cheating. And the performance gain comes from the fact that these 3 phases are actually overlapped. So you make a request, and while the attestation providers are committing their results for that request, you can start making a second request. And while the reveal phase for the first request comes in and the commit phase for the second request comes in, you can start a third request. So with this simple overlapping, you get a 3-fold performance gain. Do we have results now?
Yep, we do. Okay, so we saw Adapt make a request to the attestation provider, and then, as Xavi mentioned, attestation providers had to query this data. They had to go to Algorand's blockchain, get the information about this data, process it, make Merkle trees, submit them to the state connector system. State connector system had to validate them and come to the consensus, and the result of this, all of this process can be seen on the screen. So we can see some metadata about the request that we made. So we made a payment request to approve a payment transaction on Algorand blockchain. We can see here in a request the data requested, and in response, some of the data that the attestation provider got from the underlying blockchain. We can see, for instance, that source address and receiving address are the same. That's because I've sent algo tokens from myself to myself. We can see that spent amount is some number. This is actually in micro algos, and that received amount is a little bit more. and we can see the payment reference. This is the thing that I inputted into the Algorand wallet as a node, and we can see that it starts with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just like the string that I've put into the node. And this can be used by, let's say, F-Asset system as a payment reference, or other systems can also use these references. And together with this request and response raw data that you can see on the screen and Merkle proof that we can see on the bottom, any smart contract using the state connector can actually validate that this data was accepted by the state connector consensus protocol, and this is indicated here by these green asterisks on the screen. And we can also see that the full Merkle tree that Xavi was talking about. So if we click here, we can see that for this round, this was the Merkle hash accepted by the state connector. It had 11 leaves, and we can see that we've proven some transactions. So Algorand networks also send transactions on Bitcoin, transactions on Bitcoin network, and so on. So that's all from my side. Xavi, take it away.
Yeah, so let me summarize what did we just see. We made a transaction on the Algorand network, and then we went on the Flare network, which is totally different. We requested if that transaction did or did not happen. The state connector requested that from the attestation providers. They went, gathered information, came back, and the state connector told us that, yeah, that transaction had happened. And this has been done in a way that's decentralized. We haven't used any Flare infrastructure. The attestation providers are not under our control, and it's scalable. Now, a couple more details. I already talked about the RCR protocol. The last interesting bit is the branching protocol, which adds an additional layer of security to this. So all the validators on the Flare network use the same set of attestation providers. So all the copies of the state connector smart contract running on the Flare network, you send the queries to the same attestation providers. As a validator, as the owner, or as the operator of a Flare validator, you have the option to add local attestation providers to your list. So if you've got an attestation provider that you trust, maybe because you run it yourself, you can add it to the list of attestation providers, and it will become a local attestation providers. Now, the state connector smart contract is made in such a way that if the local attestation providers disagree with the default set, they take no action. So when the state connector collects all the answers, if there's a disagreement with the local attestation providers, they will not give any answer. Obviously, this will naturally produce a fork in the network, and your validator will halt. It will be stopped and will take no action. And this adds a second consensus round into the state connector. So first, the state connector analyzes all the attestation providers, local or not local, and runs a consensus on that. But on top of that, you can have local attestation providers that will cause a consensus fork if the network, if your validator uses a local attestation provider that disagrees with the default set. Then you can recover from that by finding out if it was your node that was if it was the local attestation provider that was wrong, or if it was the default set that was wrong, which could happen, even though that needs that 50% of the default set of attestation providers are wrong, and that requires a 51% attack on the attestation providers, which should be a rare occasion. But even in such cases, if you use a local attestation provider and you trust it, your node will be safe because it will take no action until this situation is resolved. So No matter if your attestation provider was wrong or the default set was wrong, you can be sure that your validator node won't take any action unless there's full agreement between all the involved parties. And if you are running a DApp and you are relying on your own validator node using attestation providers that you trust, this adds a lot of added security. So, to summarize, what are the main takeaways from the state connector? It brings external information into the network using a doubly secured consensus. It is a basic building block for far more powerful interoperability tools like the Ev assets and the layer cake. Very importantly, you don't need to build using the state connector to use it. It's just a regular public smart contract. You just need to call it and use it. And also, very importantly, it creates Web3 attestation, but uses Web2 level scalability. So we are very proud of this, and we think this is extremely important and will become very, very important in the scene. That's all from my side. Thanks.